Stanford University.
Let me go back and remind you, what we're going to do today is we're going to study the Ising model. I was terribly unfair to Ising last time. I looked it up and I was somewhat off base. I said that Ising failed to solve the model correctly or whatever. No, I think he solved it correctly and then thought there was a phase transition in the one-dimensional Ising model. That would be totally inexcusable. It's not exactly what happened. It wasn't that bad. He solved the one-dimensional Ising model correctly. It had been given to him by his thesis advisor as a problem, Lenz, the famous physicist Lenz. And he solved it correctly. He realized it didn't have a phase transition, but on the basis of that, he believed and wrote in his thesis that the Ising model in any dimension does not have a phase transition, and that was wrong. That was incorrect. And we're going to talk about that today. We're not going to solve the higher dimensional Ising models. They're too hard for us. They are very hard. But we will use an approximation method that's physically very intuitive. And we'll see that in higher dimensions, sufficiently high dimensions, there is a phase transition. And we'll talk about what that phase transition means. Phase transition means a sudden change in the properties of the system as you vary, for example, the temperature. But let's go slow. Let's take it in steps. Let me go back to the simple example that we studied last time. We studied a problem in which there were a collection of little magnets. Each magnet could be up or down, and there was an energy function, and the energy function differed between up and down. Let me write it again. The energy of a magnet when it's up is different than the energy of a magnet when it's down. We introduced a little variable called sigma. Sigma could be +1 or -1, +1 up, -1 of down. And we wrote an energy function. I wrote it last time as a magnetic moment mu times a magnetic field B times the thing which tells you whether the spin is up or down. I'm going to change the notation. This is too complicated. Mu times B, they just come together, and they'll always come together. So we might as well just call the product one thing. And I'm going to call the product J. Okay. Turns out that is a standard notation for what we'll be doing later. So we'll just call it J. What J stands for, I do not know. And I'm also going to make it minus. It doesn't make any difference to the physics, because it really is just a redefinition of what you mean as up and down. If the original energy favored down, then if I change the sign, it favors up. But other than that, the interchange of up and down, there really is no difference. So let's see, the way I have it now, it will favor up. It will favor sigma being positive, because if sigma is positive, the energy is negative. And of course, lowering the energy is favorable. The lower energy is favorable, especially at low temperatures. All right, so then what we did is we studied a whole group of them, and we did some combinatorics to try to calculate how many states there are with a little n up and a little m down. But we could have done something much simpler. I did it that way just to do it in some careful detail. But we can actually do something else. We've already learned that you can always think of a subsystem as a system being a small subsystem plus a heat bath. And in that case, the rest of the heat bath is just what, it just provides the heat bath, is what brings one of these systems to equilibrium. And we could just focus on one of them. We could just focus on one spin. Let's spin, I call it spin, one of these little magnets, and just assume that it is in thermal equilibrium with its environment being the rest of the magnet. All right, in that case, then we would just focus on one of these little guys, and we would write the partition function for one of them as being summation over the configurations. How many configurations are there? 2. It's going to be easy. 2 configurations, e to the minus beta times j. Sorry, it's going to be plus beta j times sigma. Why plus? Because we're supposed to write e to the minus beta times the energy. And that's what we want to calculate. What is the sigma doing there? The sigma is just telling us whether it's up or down. So there's really just 2 terms. One term, sigma is up. That gives us e to the beta j. And the other term, it's down. So it's e to the minus beta j. That's the partition function for just one spin. One of them is minus, right? One of them is minus, e to the beta j, e to the minus beta j. Okay? When we calculated it, thinking of the whole system as one system, remember the answer we got? We just got this to the nth power. In other words, we got a factor like this for each spin. So we can really short circuit all of that stuff about combinatorics and just focus on one spin at a time. And since they're independent of each other, whenever you have independent systems, you can simply take a factor, partition function factors into a factor for each system. All right, so for each little spin, we have a factor like that. Let's concentrate on that spin. That's z. And that happens to be twice the hyperbolic cosine of beta j. When we did it last time, we got twice the hyperbolic cosine of beta j raised to the number of powers of each spin. When we took the logarithm of that, which is the interesting thing, it simply becomes the sum. All right? For example, the energy, which is just the derivative of the logarithm, is nothing but the sum of the energies of the individual ones. Here we're concentrating on one spin at a time and one magnet at a time, and we'll calculate exactly the same energy for it. So let's calculate the energy. The energy can be calculated as 1 over z with a minus sign, derivative of z with respect to beta. This is the same as the derivative of the logarithm. Derivative of the logarithm of z is just 1 over z times the derivative of z. Okay, so this is not so hard. The derivative of z with respect to beta has a 2. And then what's the derivative of hyperbolic cosine? It's hyperbolic sine. So we will get a hyperbolic sine of beta times j. But then we have to differentiate the argument of the cosine, the cosh, with respect to beta, and that gives us another j. And that's it. No, not yet. We still have to divide by z. That's going to get rid of this 2 here. I look at it here and I say, that's just a numerical multiple in the partition function. I know numerical multiples don't matter, but now we see exactly why. When I divide by z, the 2 will just cancel, and I will get j sinh divided by cosh, which is called j times the hyperbolic tangent of beta j. This is the, did I?
There's a negative sign.
Minus?
Yeah, there is a negative. There is,
All the way to negative.
On the far left, you got it.
yeah,
Yeah, it's minus 1 over z at the left.
yes, I know. I know. Yeah, that's true. Okay. So that's the average energy of one of these spins. And you can also ask, what is the probability that the spin is up versus down? Or what is the average? Sigma is a thing which can take on the value +1 and -1, but what is the average sigma? Well, the energy is minus J times sigma. This is the average energy. It's pretty clear that the average sigma is just the same thing without the J. So let's write that. Well, let's first of all write that the energy, and this is the average energy, and it's now the average energy of one particle. It's not the average energy of the whole system. That's the way we're going to focus on it now. And that's equal to minus J hyperbolic tangent of beta J. I'm just rewriting the same thing. And we can also talk about the average spin and the average spin, or the average, I keep calling it spin, I should call it the magnetization, the average value of the upness or downness of the magnet. That is just equal to tangent, hyperbolic tangent of beta J. Okay, we're going to need this. We're going to need it, but let me just draw a picture of it. Hyperbolic tangent is a function which looks like this. Now, this is a hyperbolic tangent of x. And x is beta J. Okay, so this is a hyperbolic tangent of beta J. J is a number. We could have set J equal to 1. I don't even know why I bothered keeping the J. I could have left it equal to 1. It's tangent of something proportional to the inverse temperature. Okay. The slope of the hyperbolic tangent over here is 1. It just has a unit slope over here. And then it asymptotically becomes flat and goes to a constant, namely 1 over here, and minus 1 over here. Okay, so let's think about what that says. If beta is very, very large, that means low temperature, and let's suppose J is positive, then beta J is very large and positive. That's way out here. And what it's telling us is that the spin will point up with probability very, very close to 1. The value here is 1, and the average of the spin is very close to 1. The only way it can be close to 1, if the only values it can take are minus 1 and 1, the only way the average can be really close to 1 is if the probability is almost exclusively for it to be up. And that's what's going on out here. On the other hand, we can also look at the negative axis. Beta, we don't want beta to be negative. Beta is the inverse temperature, but J can be negative. That just corresponds to having put in the other sign, and all it does is flip up and down. So, as you might expect, what goes on way out here, when beta J is very negative, is the spin wants to point in the opposite direction. The magnet wants to point in the opposite direction, and that's all that's happening here. Otherwise, the two sides are completely symmetric. Okay. Notice that at the origin, now where is the origin here? The origin means beta J equals 0. That means very high temperature. Very high temperature, beta is the inverse temperature. Very high temperature, the temperature is just so high that it's constantly being kicked around, and it overcomes, the temperature just overcomes any bias for it to be up or down. And so on the average, it's just plain 0. Okay, so this was a very, very simple system. Now we want to come to the next most complicated magnet. And it's the one that we talked about it, but let's go back to it. The Ising model, which is, and the one-dimensional Ising model, which is at each point along a one-dimensional array, there's a sigma. Sigma is either up or down. And the new thing is that the energy depends on the relationship between neighboring ones. The energy is now the sum. Now, this is not the one particle energy. This is the total energy. You know, we better keep in mind that this thing over here is the energy of just one spin, not the whole thing. Okay, now I'm actually studying the whole shebang. The energy is the sum over all of them of the product of neighbors. Let's call it sigma I times sigma I plus 1. That means you go to each site and you multiply the spin by the spin or the the value of its neighbor. We'll also put a j there. The j is just a numerical constant, which I'm sort of sorry I introduced, but let's leave it there. Since I started. And I'm also going to put a minus sign there. Okay, that's the energy. The minus sign means that it favors them being parallel. You want to lower the energy as much as possible, and you lower the energy by having them all parallel. If they're all parallel, the product of the spins is all equal to plus 1, and with the minus sign that I included here, the way to lower the energy is to make them all parallel. What would happen if I put plus j in here? Oh, first of all, let's imagine now the ground state of this system. What is the ground state of this system like? The ground state will have the lowest energy, will have them all lined up. But in which direction? Up or down? There's two ground states, and they're the same. They have the same energy, all ups or all downs. Now, what would happen if we change the sign of j? In other words, make it plus j sigma I plus 1. Is it really a different system? No, it's really the same system. And all you have to do to see it's the same system is to redefine every other spin by changing its sign. On every other spin, what you called up, you now call down. You redefine the variable. And then what you find out is the ground state wants to have them all anti-parallel. Up, down, up, down, up, down, up, down. But it's really mathematically an identical system. And again, there are two states. This particle could be up, in which case this one will be down, in which case this will be up, in which case this will be down, or the opposite. So it's mathematically identical. Yeah.
Fix your mic real quick.
No, you're missing the point of this. This is in place of my coffee. Okay. Good. And what we want to calculate is the usual thing. We want to calculate our friend, the partition function, our best friend, the partition function. And what is that? That's e to the minus sum. Now, what are we summing over? We're going to be summing over all possible configurations. Any one of these could be up or down, and that's a huge sum. All right? But we're going to do it. E sum e to the minus j summation sigma I plus 1. It looks terrible. It looks very hard. Oops, I left out something. Beta, the temperature, the inverse temperature. So there's a beta there. Oh.
Did you say that there's no external field?
No what?
Did you say there's no external magnetic field?
No external magnet for the moment, yeah. No external magnet. We could do it with an external magnet too, and we will discuss that at some point. But for the moment, no external magnet. And this is the problem we want to do. Okay, let me first organize a question that we can ask. I would like to know the answer to the following question. Supposing I know that the magnet over here is up. Then I could ask, knowing that the magnet over here is up, then what is the probability that n links down the chain here, it's also up? That's called a correlation function. It's the conditional probability that if we know that a spin over here is up, what's the probability at some other place that it's also up. Could ask it a different way. You could ask, what is the, it's the same question really, what is the average of the product of spins at two different locations? What is the average? Now you might think, in this case you'd be right, you might think that if you go far enough down the chain that a spin being up over here would have very little effect farther down the chain, and you might expect then that the average of the product would be 0, because whatever this spin is up here, this one has equal likelihood to be up or down. You might guess, but you might be wrong too. There might be an effect of just having one spin up over here that would propagate all the ways through the system and tell you that there's a net bias throughout the whole sample. You could diagnose that by looking at the average property, the average value of the spin over here, let's call that at point I, times the spin at I plus n, where n is n units down the chain. If there does exist this memory, this kind of memory, where if this spin is up, it biases the system all the ways to infinity, then this would not go to 0 with large distances. If, on the other hand, that bias does go to 0, then this one being up would not bias this one, and on the average the product would be 0. So this is an interesting diagnostic test of the effectiveness of one spin being up on its neighbors and how far that propagates down the chain. Okay, so let's see if we can guess what the answer is for this case. Think of this instead of as a spin chain or a magnet. Think of it as a game of telephone. You know the game of telephone where you whisper to your neighbor. So we have a long chain of people, and a message is going to start at one end somewhere. So it doesn't have to be at the end. It could be over here, and the message is going to be a very simple message, either 0 or 1. We're not going to make fancy messages like the kids who play this game. You know, my dog had a heart attack, and therefore I'm off dog food for the rest of my life. I don't know what, but no, just 0 or 1. 0 or 1. And people hear pretty well, and people talk pretty well among this group of people, but the fidelity is not absolutely perfect. It's pretty good, but it's not absolutely perfect. All right? The question is, how far down the chain does the signal propagate before it gets lost, before it just becomes equally likely far down the chain that the person agrees with the starting point or disagrees? And the answer is, no matter how good the fidelity, as long as it's not absolutely perfect, you'll lose memory sufficiently far down. If there's a probability for an error of 1% in each time, then the probability for no error is 99%. But then to go 2 units down the chain, it's 99% of 99%, and that's 0.981, right? 100 minus 1 squared, which is 100 squared minus twice 100 plus 1. Right, 0.981.
I just said the binomial theorem.
Binomial theorem. 0.981. I'm not going to try to do the next one. But, you know, each time it goes down by a factor of 0.99. And if you go far enough down the chain, that product will get arbitrarily small. And so the probability 100 units down the chain that the signal is remembered with good fidelity is 0. Well, not 0. 100 units down the chain is about where it begins to fail, seriously. 10,000 units down the chain, basically no memory. The same is true. It's the same thing here. If this spin is up, and there's no signal now, but there is a bias, and the bias is the energy bias here, that the system prefers a lower energy. At 0 temperature, zero temperature is like the perfectly accurate signal, infinite fidelity. That's like the situation where there's no loss whatever, and then everybody just lines up. If this gentleman says up, then this lady down here will say up. If this gentleman says down, this lady will say down. So there's perfect correlation. But if there's any slight infidelity, it's not the word I was looking for, but right, yeah, you know what, it will fade. And that's what will happen here. That's what will happen here. And Ising got that right. He got that right. Okay, so let's see if we can calculate, what's the trick? There is a trick. And the trick is a marvelous trick. I imagine it was invented by Ising, I don't know. And the trick was to focus, instead of on the spins, on the links between the spins. So here is what I imagine Ising said to himself. He said, look, there are two possible values that the first spin, we're going to imagine for the moment that the chain is finite. Let's imagine the chain is finite, and then we'll let it get very big, but let the chain be finite, and the first spin can either be up or down. Let's start by assuming it's up, and later on we'll put back the configurations where it's down. So we're going to write the partition function as a sum of two terms. In the first term, the first one is up, and in the second term, the first one is down. But let's concentrate on the one where this spin is up to begin with. This one at the beginning of the chain is up. All right, then I can either use as my information about this next spin here, I can either use the value of the spin, or I can talk about the product of this spin times this one. Okay. For example, let's take sigma 1 times sigma 2. Since sigma 1 is known to be up, sigma 1 times sigma 2 will tell you everything you want to know about sigma 2. So let's call that mu 1. And what is it? It's a variable that has to do with the relationship between the first spin and the second spin. Okay. It's a variable which has to do with the relation, but if you know it, then you know what the second spin is. Okay. What about the next one? Let's introduce sigma 2 times sigma 3 and call that mu 2. That's telling you, if you like, the state of the link between. Think of, instead of thinking of the spins, think of the links. The links have two possibilities, either parallel or anti-parallel. That would tell you nothing about any individual spin unless you knew the first one was up. If you know the first one is up, and you know mu 1, then you know sigma 2. Supposing you also know mu 1 and mu 2. Then you know what sigma 3 is. And in fact, sigma 3 will just be mu 1 times mu 2. Why is that? If mu 1 is up, mu 1 times mu 2, sigma 2 squared is 1. Sigma 2 is either plus or minus 1. So multiplying it by itself gives you 1, and you find out that sigma 3 is mu 1 times mu 2. So if you know mu 1 and you know mu 2, you know the first three spins. Obviously, if you know the mu's for all of the links in between, you know all the spins. And there's no redundancy, there's no double counting. As long as you know that that first spin is up, then there's no double counting. It is equally good to know the mu's, which live, so to speak, on the bonds between the spins, as it is to know the spins themselves. Okay. But that's very useful. Why? Because the energy is just made up out of these bond variables. Bond meaning the relationship between neighbors. So here's what we can write. We can write that this energy is just the sum over the bonds. Let's call them the bonds, the neighboring bonds. The sum over the bonds, first bond, second bond. Notice there's one fewer bond than there are particles. Okay? but it's sum over the bonds of mu I. In other words, it's also a sum over I. Let's just call it sum over I of mu I. In other words, the first bond variable, the second bond variable, and so forth, times minus j. We're not even multiplying anything anymore. It's just the individual bonds, and the individual bonds are all independent. There are no relationships between them. As long as you know that that first spin is up, there are no relationship between them, among them, and it is as good to know the mu's as it is to know the sigmas. So you can substitute, you can substitute the sum over spins. You can substitute for it the sum over the values of the bonds. What are the possible values of the bonds? +1 and -1. Now it's +1 if they're aligned and -1 if they're anti-aligned. So we can write this as z instead of the sum over the spins. So this is sum over the spins. It's sum over the bond variables, e to the minus j beta times the ith bond. Now, in fact, I'm going to tell you that it's twice this answer. Why is it twice that answer?
Can start with the other.
Because we could have started with the first bond down. But a factor of 2 is no big deal in a partition function. So the other thing is to remember, if the number of magnets is very large, it doesn't matter much. But we should remember that there's one fewer bond than spins. Other than that, this has now reduced to exactly this problem, except that except mu in this here is called sigma. It's a sum over uncoupled individual bonds, and it has exactly the same form as the partition function for the simpler magnet. But remember now, a mu does not stand for the value of a magnet. It stands for the relationship between two magnets, between two neighbors. But still, we know the partition function. There it is. Same thing. Twice cosh beta j. Okay, so let's write it in full. It's twice this. So we're going to have an extra factor of 2 on the outside of it. Then twice cosh beta j. And now let me put in the thing which I didn't put here, which was if I have a lot of spins, this gets raised to the nth power. So this is now to the number of bonds, which is the same as the number of magnets minus 1. That minus 1 is not going to... Okay, so are you with me? Everybody with me?
I have a question, please.
Yeah.
In the first expression of z, where you had sigma I plus 1, there was a sum. The sum is gone in the lower one. Why is that?
Sorry, where are you?
The last line and the one before.
Oh, sorry. No, there's certainly a sum here. Excuse me. There is a sum here. Is this what you're talking about?
Yeah.
Minus the sum over I of that. All right, but the point is, of course, that
That makes
some...
the argument of the cosine also the sum. Is that-
No. That sum. Remember that a sum and an exponent just means a product.
Got it.
Right. So this is just it's a sum over each individual bond. This thing just factorizes into separate sums for each one of the bonds. Right. So all it is, each one of the bonds, the energy is a sum. That means the Boltzmann factor here is a product. And you're just summing over each spin individually, not each spin, each bond individually. It just factorizes. If you have trouble seeing exactly why it factorizes, the thing to do is to write it down for 3 spins with 2 bonds. Okay, just write it down with 3 spins, 2 bonds, write down the full expression, and you'll see very quickly why it factorizes.
So that's what ultimately yields the n in the exponent.
That's what yields the end
The
of the
sum.
exponent. Yeah, that's right. That's right. And we actually did it both ways. We did it last time for the single spin, but for the problem on the top, we did it both ways. We did it by thinking of the whole system and counting all the configurations, and then later we just did it for 1 spin and then took it to the nth power. And that's a legitimate thing to do. All right, so we've reduced it to exactly the same problem as before. The only difference is the physical meaning of the degrees of freedom here is a little bit different. Okay. Now, what is the average? Let's not ask about the average of the spin. Let's ask of the average of mu, the average of the product of neighboring spins. The average of the product of neighboring spins anywhere along the chain is going to be exactly the same calculation as this. So let's write it down. The average, we could either write it as any given mu, or we can write it as the average of sigma I plus 1. That's going to be tanh beta j. You know, I think with my current setup, it's tanh beta j. Tanh beta j, that's correct. All right. So it's not 0. There's the product of them. The fact that it's not 0 and positive, we're taking j to be positive. The fact that it's non-zero and positive tells us that there's a net tendency for I to line up in the same direction, the I plus first one. That's the same thing as saying there's a bias for mu to be positive. There's a bias. If the first spin is found up, the next one has a better than even chance of also being found up. And what's the better than even chance? Basically tanh beta j. Okay, so this tells us the correlation between neighbors. And there is a correlation between neighbors. But let's now go far down the line. Let's now ask exactly the question which I asked when we started. What's the correlation between the first spin, the ith spin over here, and 1 n units down the chain? How are we going to get at that? Well, the answer is very simple. You just write, let's use this blackboard over here. Here's what we want to calculate. The average of sigma I, times sigma I plus n. I'm leaving a gap in there because I want to write some things. Okay. What I'm going to put in here is sigma I plus 1, sigma I plus 1. What's sigma I plus 1 times sigma I plus 1? 1. I didn't do anything. And then I'm going to put in sigma I plus 2, sigma I plus 2, and so forth until I get to the last one here. But now I can write this as the product mu1, mu2, mu3, ... down to mu. Now, how many is it? How many do I have going down there? Is it n minus 1? I think it's n minus 1, right? Where mu1 means this thing over here. The next mu2 is this thing over here. Mu3 is the next one here, until we get down to the end of the chain. All right, so now all we want to know is the average of the product of these. But all of the mu's are independent of each other. The energy is the sum of the energies, the problem completely factorized. The average of any one of the mu's is tanh beta j. So what's the answer? The answer is tanh beta j to the power n minus 1. In other words, the number of steps between the first spin and the last one. This formula is expressing exactly the idea of the game of telephone, that if you lose, tangent beta j is first of all always less than 1, except when beta is infinite. That's absolute zero temperature. Zero temperature, perfect fidelity, this is 1, and no matter how far down the line you go, the answer will be 1, which is the statement that at zero temperature, if you know that this one is lined up, every one of them is lined up. There are only two possibilities, everybody lined up this way or everybody lined up that way. And in either case, the product is 1. But if there's any loss of fidelity at all, which means in this case the temperature is not absolutely 0, then this tangent beta j is less than 1, and each time you go another step, you lose a factor of tangent beta j. That's like losing this 99% of 99%. And so, whether you like it or not, when you go sufficiently far down the chain, this correlation function will become arbitrarily small. There will be no or negligible exponentially small memory. This is an exponential function of n, a number less than 1, raised to the nth power. So the correlation falls exponentially with n, with distance. Yeah.
I thought the correlation function was just sigma 1 times sigma, or sigma I times sigma I
The
plus
average
n.
of it. The average of it.
Right, right. But I mean, it doesn't have all these ones in between that you have here, right?
No, it's, I did a trick. I put 1s in here. I put 1s in there. Why? Because I wanted to re-express it in terms of the things which I knew, which are the mu's. So it's a marvelous trick. You concentrate on the bonds instead of the spins themselves. I don't know if this was invented by Ising or not. If it is, he deserves some applause. Right. Okay. This, incidentally, is a pattern. This, incidentally, is called a duality. In modern physics, this could be thought of as the first duality, equivalence of different systems. We found an equivalence between a theory of spins which are connected nearest neighbor with another theory up there of just spins which are uncoupled to each other. With a change of variables. A clever change of variables which basically took sites to bonds, which interchanged sites and bonds. Sites are the points of the lattice, bonds are the sites and links of the things we would say. That's the first example of a duality between different statistical mechanical systems.
Edges and vertices.
Yeah, edges and vertices. It's not always edges and vertices, but in this case it is.
So at one point you said there was a bias to anti-alignment because that's a lower energy. That's always -1.
No, it's the lower energy is when they're aligned. I think.
That's the part I missed.
Yeah, okay. If they're aligned, the energy is negative. That's why I put the minus
So the
sign
minus
here.
sign means this is a lower energy state than this,
Mhm.
which is not what a magnet.
Oh. That's what a ferromagnet does. Ferromagnets, the magnets line up.
Right.
It's a matter of very intricate detail whether the little elementary magnets in a material prefer to align or anti-align. Most of the times they prefer to anti-align, but in iron they prefer to align. And as I said, it's a matter of detail. And those are details we're not going to go into. Okay. Okay, so we found out some things about the one-dimensional Ising model. And what we found out is that it's never magnetized. Magnetized, except at 0 temperature. Magnetized can translate into the statement that there's this long-range memory. If one spin is up, all the others will be biased to up. That's called magnetization. And it's equivalent, in fact, to the statement that if you put a tiny, tiny magnetic field on the system to bias it, it will cause everything to line up. We'll see that. We're going to see that in a little calculation in a little while. Okay, this is a boring system. Has no phase transition. It does exactly what you might have expected it to do. Correlations fade as you go down the line. And the reason is simple. It's the same reason as in the game of telephone. There's a statistical probability that you'll make an error. Once you make an error, you start over again with a new message, and you wait until you make another error, and then you start over again, and that's the way it goes. Nevertheless, there will be some clumping of a tendency for clumps of a thing. Just like in the game of telephone, there will be long stretches where of agreement, long stretches of agreement, and then statistically, on the average, every so often, a switch. But then long chain of agreement again, and then a switch. Okay. So, yeah. At high temperatures, then that's like the fidelity being very bad. Infinite temperature is like the situation where then you just can't hear your neighbor. You get no information from your neighbor, so you wind up, whatever your neighbor says, making a random guess. In that case, let's see. That's the case. Beta equals 0. Tangent of 0 is 0. So that's a statement that there's not even correlation between the nearest neighbors. Okay. Excuse me. Okay, boring system. How do you make it more interesting? Well, what's wrong is the dimension is too low. In a one-dimensional chain, once you make a mistake, that next fellow doesn't have any support telling what the right answer is, because he just gets his message from the previous person. Okay, what about higher dimensions? So now instead of playing telephone, let's play a different game. Kevin over here starts a message, and he sends the message correctly to the fellow on back of him, the fellow to the left of him. And then they each send a message to all their neighbors. In particular, they will wind up sending a message to the person that Kevin has already sent a message to. He's going to use his judgment. And in particular, as this spreads throughout here, people are getting messages from different sides. They're going to be able to make their judgments. In fact, everybody will get basically 4 messages from all the people around them. If one of those messages happens to be wrong, but 3 of them are right, what'll he do? He'll do what computer scientists call error correction. Error correction just means he will take the majority vote. This works much, much better. And in fact, if the fidelity is good, the bias of the initial message will spread throughout and off to infinity. Same thing happens in the two-dimensional Ising model, that the bias of any one spin will bias the rest of the, and in fact, we could just say, putting a little magnetic field on one spin in 2 dimensions will bias the whole sample. This is not completely obvious. When I thought about it a little bit, I realized I can't prove that. I actually can prove it, but I can't prove it in an easy way. The way I prove it is by going through the analysis of the two-dimensional Ising model, which I know how to do. But the fact that Ising got it wrong, it wasn't, there were worse things in the world. He got that wrong. And in fact, he thought it was wrong in every dimension. But if you think about it for a minute, you realize that it's very dimension dependent. Why is it dimension dependent? Well, in one dimension, each person has 2 neighbors. That's not very many. It doesn't have much of a support system. He gets the message really only from one direction. How many neighbors does a 2-dimensional system have? 4 if it's a square lattice. So that means you're getting messages from 4 people. You have a pretty good chance of getting the right answer, even if the fidelity is not so good, if you use some weighting procedures such as taking the majority. You do pretty well. You do much, much better than if you were just getting the message from one person. How about in 3 dimensions? You have 6 neighbors. How about 10,000 dimensions? Whatever it is, 20,000 neighbors. I used to have this friend, Artie Harris. Artie Harris was the first black Mr. America. Anything you ask him, anything you tell him, he would say, 100 men can't be wrong. I don't know what he had in mind, but in high dimensions, it's true. 100 neighbors won't be wrong very often. Fluctuations among large numbers of variables tend to be very small in comparison with the net, if you have 100 pluses or minus ones, then the average fluctuation will be much smaller than the net magnitude of the square root of n kind of statistics. So you have a much better shot at being able to propagate the information of one spin throughout the entire lattice, the higher the dimensionality. So that leads us to ask the question, what would the Ising model be like in very high dimensions? Some limiting number of dimensions, 10,000 or whatever it is, and what can we say about what can we say about it? Okay.
Does this correspond to any sort of physical phenomenon? Higher than 3-dimension Ising model?
It turns out 2 is high enough. It turns out that that 2 behaves like 10,000. It's curious. 2 is high enough. Now to answer the question, where does n, or the number of dimensions d, become large enough to be able to trust large dimensions is hard. Okay. 3 is very large in this game. But that's as a matter of computation, having solved it or solved it numerically or whatever, we know that 3 is a very large dimension. So the answer is, which is not obvious, is that only the one-dimensional Ising model does not have a transition, does not have this tendency. But that's not something that could have predicted easily. What could have predicted easily, not too hard, and we're going to do it tonight, is that in sufficiently high dimensions is an awfully good argument to say that, there's a transition. At high temperatures, everything's random, and as you lower the temperatures, everybody wants to line up, and that lineup propagates throughout the system to infinity. Okay, the trick that I'm going to use, there are many tricks to do this with, I'm going to use something called mean field approximation. I'll tell you what it is. Each site is surrounded by how many neighbors? We're going to do d dimensions. D dimensions. D stands for dimension. Each site is surrounded by 2d neighbors. We're going to imagine D is very large. And because D is very large, you can imagine that all of the neighbors define a field, let's call it a field, whose fluctuation is much smaller than its average value. If you have a large number of variables and they're biased, so that they all add up to something of order the number of variables, the fluctuations around that will typically be much smaller than the bias. Okay, so that's what we're going to do. Let's focus on that spin. And all the others we're going to make an approximation about. Let's focus on this spin and write its energy. Just the energy of this one spin. The energy of this one spin is minus j times sigma times the sum of the neighboring spins all around it. Okay, so this is the sum of the neighboring spins, the sum of the neighbors, N-E-I-G-H-B-O-R. Now let's suppose that there is a bit of bias and that the average of the spins is not 0. Of course, we're going to check that. That's what we're going to try to check. Let's suppose that the average of the... I'm going to write a formula. The formula would allow the spin to be 0 too, but let's suppose throughout this lattice that the spin has an average called sigma. Maybe I can make it simpler. Let's call it sigma bar. The average spin, and we don't know what it is. It might be 0, might be plus, might be minus. We don't know what it is. But I'm going to replace the sum over neighbors here by simply twice d times the average. Now that's a pretty good approximation if the number of neighbors is large. And the larger the number of neighbors, the better the approximation. Right. When we have large numbers, as a typical rule, we're allowed to average and the fluctuations are small. So we can replace this by minus j, 2d because there are 2d neighbors, minus 2d j, and not sigma times its neighbors, but the particular spin at this point times the average spin. That's the energy of one particular spin sitting in the bath or in the field of all the others. This is called mean field approximation. Mean not being in the sense of nasty, but mean in the sense of average. And field now being the field experienced by one spin in the field of all the others. So this is the energy of this particular spin over here. And now what we can do with it is do the partition function of that one spin. Okay. In fact, we don't even need to do the partition function. We know how to do the partition function. It's exactly the same calculation we did over here, except instead of writing j, we will write 2d times j. Exactly the same calculation as here, except every place we saw j in the upper calculation, we will have 2d times j. So I can immediately write down what the average spin is. I can immediately write down that the average of this spin, this one over here, let's call it sigma double bar for a minute. The double bar indicates that I'm talking about this one. All right? Its average spin is just going to be tanh. Now it's not going to be beta j. It's going to be beta times 2dj times sigma bar. What did I say? Did I say every place that we saw j we should stick 2dj? No. Every place we see j, we should stick this whole thing. 2dj times sigma bar. This spin over here is moving in the background of all these others, and the others all constitute a constant field that we just called sigma bar. So the answer is going to be the average of this spin is hyperbolic tangent of 2dj sigma bar. Beta, thank you. Two beta dj sigma bar. Let me write it over again. Let's go to this blackboard over here and write it nice and clear. Sigma double bar, the average of this particular spin, is going to be hyperbolic tangent of 2 beta dj times sigma bar. Now, this mean field approximation is also sometimes called self-consistent field approximation. Why self-consistent? Well, self-consistent because, hopefully self-consistent, because this spin over here is no different than all the others. It's just one of the many spins in the system. And if all of these have an average equal to sigma bar, the physical intuition would require that you would say that the one over here also has the same spin, same average. That's got to do with translation invariance. It's got to do with that every one is really the same as every other one for a big sample. And so the self-consistent field theory is to say that sigma double bar is the same as sigma bar. We have an equation. We now have an equation for what sigma bar is. It's an equation. Tells us what, well, it could tell us what sigma bar is.
It's just a simple proportionality. I mean, you're saying sigma bar is proportional to itself?
No, saying sigma bar is proportional.
Inside the argument.
Yeah. It's inside the. I put the bracket around here to indicate that this was a constant. Okay, it's a constant with proportional to the inverse temperature, but this is inside the bracket. Sigma bar is inside the bracket. So this is an implicit equation for sigma bar. We want to solve it.
Does that mean high temperature?
This is for all this equation would apply to all temperatures.
When the variable is almost equal to the tangent, doesn't that mean very small variable?
No. Tangent can go anywhere from 0 to 1. Tangent can go anywhere from -1 to 1. Okay. So the question is, how do we solve this? And how do we get an intuition?
Question?
Yeah.
So before, I would have expected you to have written angle bracket sigma equal tang.
Yeah.
Is the single bar the same as?
Yeah. I just didn't feel like writing angle brackets. You
Okay.
didn't hear me when I said it.
Okay, I'm sorry.
No.
Yeah.
I decided to use the bar notation instead of the bracket notation.
Another question. I'm a little confused about your D. I can see how you could have 3 or 4, but if you talk about greater than 4, are you talking about nearest neighbor, next nearest neighbor?
No, nearest neighbor.
These are all nearest neighbors?
Yeah. How many nearest neighbors does the lattice in D dimensions have? In 1 dimension, 2. In 2 dimensions, 4. In 3 dimensions, 6. How many in 4 dimensions? 8.
If
So
you
just assume
included
D is
next
the largest
nearest
number of
neighbors,
dimensions of space.
would
Yeah.
that be equivalent to getting a higher dimension?
Yeah. Yes, next nearest neighbors would go in the same direction as making a higher dimension, absolutely.
But you'd have a scale factor there, wouldn't you?
Hmm?
Wouldn't you have a scale factor for next nearest neighbor and next nearest neighbor? Don't you have some geometry?
Yeah, sure. So we picked a particular situation and study it as a function of dimension. We could study it as a function of the nature of second nearest neighbor couplings, third nearest neighbor couplings. We could do all these things. This is just one way of making a spin have a lot of nearest neighbors. The physics of high dimensions is not something we realize in the laboratory. We do this all the time. We want to prove something about a system. It's a little too hard. We can't get our hands on it, but we can go to some limit where it becomes much easier. We prove it in the limit. We haven't proved it for the physical case of interest, but at least we can prove that somewheres between, in this case, 1 dimension and 100,000 dimensions, a certain new kind of behavior happens that wasn't present in 1 dimension. Once we see how that works, we can then ask, where does the change happen? And in this case, it happens between 1 and 2. Okay, but this is a nice, simple example where you can see what happens physically without having to solve a difficult mathematical problem when D is very large. Okay, so let's try to solve this equation. The first thing to do is to change variables. I know you hate to change variables, but there's a good reason. Tanh of a complicated thing. I don't want a complicated thing in tanh. That's a nuisance. So I'm going to say 2 beta dj. This is a number. 2 beta dj. They're all numbers for our purposes right now. This is just a number. I'm going to change variables so that 2 beta dj times sigma bar is itself a variable. And I'm going to call it y. Why? Because. Tanh on the left side. What about the right side? The right side is just y divided by 2 beta dj. Okay? Now, to solve this equation, I'm just going to graph both sides and see where they intersect. Okay? The crudest way to solve an equation, just draw a graph of both sides and see where they intersect. This is y. The vertical axis is just tanh of y. Okay? And here's the tanh function. Now the left-hand side is just a linear function of y. Everything else in here, instead of calling this beta, let's take 1 over it and put the temperature in the numerator. It's the temperature. Okay. So let's plot the left-hand side here for different values of the temperature. Let's use another color and plot it for different values of the temperature. First of all, let's go to very high temperature. At very high temperature, this is a very steep function. Of course, D is a large number, so how big large temperature is may depend on D. But eventually you get to a large enough temperature that the slope of this side is large. So we go to some very large temperature and the slope is high, and there's no intersection except the intersection at y equals 0. The only possible answer to the self-consistent field theory is that y equals 0. But what is y? Y is proportional to the average of sigma. So we learned, first of all, that at very high temperature, that the average of sigma must be 0, as expected. That's not too surprising. Okay. But now let's start lowering the temperature. As you lower the temperature, the slope of this curve decreases. There is a point where the slope is actually equal to 1. And the red line here is tangent to the tanh. Tangent to the tanh. What a lovely idea. It's tangent to the tanh here. Where does that happen? That happens when the slope, that happens when the temperature, let's write it down, when the temperature over twice dj is equal to 1. That's when the slope or when the temperature is twice dJ. Something happens. Temperature is equal to twice dJ. When you go beyond that, there's now some new solutions. As soon as you get past 1, could be over here. Just as this line rotates, soon as it gets past slope 1, there's now solutions along here. There's also a solution over here and down here, but let's assume that J is positive. Just to be clear, let's assume J is positive. So we're only interested in the right-hand side here. Now there are new solutions, and for the new solutions, y is not equal to 0, and therefore the average of sigma is not equal to 0. In other words, the system has an overall global average of spin pointing all in the same direction. And that's the phenomenon of magnetization. What happens here is called a phase transition. Beyond that point, there's a net magnetization. There's an average magnetization, an average field that just permeates the whole system forever. Now wait a minute. You say, hold on. What about this solution? How do I know that the right solution wasn't the one at the origin? For any value of the constants, the red curve does intersect the black curve at the origin. So how do I know which one is right? Okay. How do I know which one is right? Well, we're going to do a little calculation. I don't think we'll do it tonight, maybe next time, where we're going to add to this problem a teeny little magnetic field that biases the system. And we're going to discover that the teeniest little magnetic field will tell us that we should be on this branch, on this branch of the solution and not here. But we can see it another way. Let's go to 0 temperature. 0 temperature is way out here. And we know what to expect at 0 temperature. At 0 temperature, we expect alignment. We expect everybody to align, and so we expect these things to lock into a parallel configuration. It's way out here, everybody aligned. And as you lower the temperature, you slide in along this line until you get to the transition point here. And beyond the transition, lower temperature than the transition point, the only solution is at the origin. So that's the nature of a phase transition, which we'll talk about a little more. But I think I won't try to do it tonight. Next time, we will put, actually it's pretty easy. It's pretty easy from this point to put a little magnetic field in. Is everybody up to a little magnetic field?
Can I ask a quick question, please?
Yeah.
What happens if you put d equal 1? Why does it stop working?
It's just too low. The only guarantee is that at sufficiently high dimension it works.
We know Ising doesn't work for 1.
Yeah.
And I thought there is a mathematical, beautiful, something happens when you make d equal 1. Something blows up.
It does. It does. I'll tell you what it is. Okay, let's think. Yeah. Let's go to absolute 0 temperature first. Okay. Absolute 0 temperature, everybody wants to align. Now let's imagine writing the partition function as a sum over all the configurations. How can we enumerate the configurations starting with this configuration? Well, we can enumerate it by the number of spins that are flipped relative to this configuration. So we could start with in writing the partition function. In writing the partition function, we would start with this configuration, okay, e to the minus beta times the energy of this configuration. At low temperatures, starting at low temperatures, this would be the dominant configuration. Then we raise the temperature a little tiny bit, and some new configurations start to become important. Okay? For example, 1 spin flipped. Let's flip 1 spin. In fact, let's do the same thing over here. Do the same thing over here in 2 dimensions. Here we have plus, 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 etc. as our starting point. Everybody's pointing in the same direction. Now let's ask what the next state is, next in energy. This is the lowest energy state. The energy is stored in the bonds. It's sigma dot sigma, which is the energy of a pair of neighbors. What happens if you flip one spin? Instead of being plus, let's make this one negative. How much energy do we get? How many bonds have we broken? A broken bond means that instead of having parallel, we have anti-parallel. How many bonds have you broken?
4.
Right. And right. And how many places are there that you can do that? Basically, on each site. Each site. The number of places you can do that is the total number of sites. Okay, so that means there's a number of configurations that you can add in with 4 extra units of energy. Now, supposing you want to break, or we want to flip 2 spins, the next configuration, what's the next configuration? We flip 2 spins. What's the energy of that configuration? Can you tell? How many broken bonds are there? Okay, let's see which bonds are broken. The minus-minus bond is not broken. They're parallel. Okay? This one's broken, this one's broken, that one's broken, this one's broken, this one's broken, and this one's broken. 1, 2, 3, 4, 5, 6. So I've increased the energy by 6 units of each broken bond cost a certain amount of energy. I've now increased the energy by 6 broken bonds. Okay? What would have happened if I would have put the minus sign way out here, far away? Then I get 8. Okay? So each time I increase the number of flipped spins, it costs me something. In the Boltzmann factor, e to the minus beta times the energy goes up. Each time I flip another spin, the energy goes up. Okay, now let's compare that with a one-dimensional case. How much energy does it cost to flip 1 spin? How many bonds get broken? 2, right? How about to flip 2 spins? If they're adjacent, it's still just 2. How about 3 spins? You can flip any number of them and still only cost 2 units of energy. So, yes, I picked them adjacent. That means there's a lot of configurations, all with the same energy. Much, much more here. Here, in this case, the number of configurations with 4 extra units of energy would be just proportional to the number of sites. How about here? The number of configurations with 2 extra units of energy. That's proportional to the square of the number of sites. It's proportional to the square of the number of sites because you can pick any 2 bonds and flip all the spins in between them. So there's just a lot of configurations where a lot of spins are flipped. That's why it's unstable with respect to flipping lots and lots of spins. And as soon as the temperature is turned on, it costs very little energy to flip whole big loads of them. Whereas here, to flip 1 costs you some energy. Okay, that's the same as there. But to flip 2 costs you more energy than 1. That's the basic mathematical thing that's going on. And
If you just simply look at this equation that you got from this mean field thing, you don't see any difference between d equals 1 and d equals 2. So,
Well, except in the factor of d there. Well, there is you see the difference in the coefficient here. All right, let's look
right,
at
but I
it.
mean, you still have this phase transition phenomenon.
Yeah.
But is that means
No, exactly. You don't see the difference between 1 and 2, and that's right.
But isn't it correct that the mean field?
Why are you confused? This only made sense if d was large.
over here does,
Yeah.
but I'm trying to relate it back to this.
No, the formula only makes sense if d is large. Formula only makes sense. The whole physics, the whole argument only makes sense.
So how do you turn on the little magnetic field?
What's that?
How
Okay.
do you turn on a little magnetic
All right.
field?
So now let's turn on a tiny magnetic field. To do that, where's our energy function? Here's our energy function over here. I'm still concentrating on one spin, but now in addition, we imagine the whole system has an external magnetic field. That means that each spin has an extra energy not related to its neighbors, but just whether it's up or down. Let's call the magnetic field B. Times sigma. With B times sigma, it's favoring down. If B is positive, it's favoring down, but we're going to imagine eventually that B is very small. This is the extra energy not related to its neighbors, but and each of the spins has this extra term here. Okay. And that's the whole difference. The whole difference is instead of tanh being tanh of 2dj sigma bar, it's going to be tanh of 2dj sigma bar plus b. Notice sigma, sigma factors out. Sigma, put some brackets around here. It's exactly the same problem, except we've replaced 2dj sigma bar being a number, we've replaced it by adding a b. Okay. What that does is it adds to the variable y, it adds plus b times beta, I believe. We want e times, which is the sign? Which sign do I want? I think I want to favor, I guess I want to favor up spin, so let's put a minus there. Let's put a minus that favors up spin. Yeah, okay, this favors up spin. Then I guess it looks like this. Yeah. So this is a new equation. Let's compare it with the old one. We'll draw the picture. We're just going to plot again the right hand. Does everybody see what I did? Yeah, we just added a constant to the argument here. That's all. It's very simple. Okay, what does that do to the tanh function?
Don't you have to have the B on the left-hand side too?
A what?
Yeah,
Okay, doesn't that shift the left-hand side?
No. No.
Why? That plus.
No, the left-hand side, no. The left-hand side was the calculation of the average spin in the background field. Here's the background field now. We calculate the average spin in that background field. We call it,
Well, it should be tanh to 2 beta dj sigma bar plus. Is there-
exactly right. What we did was we took this new energy function, calculated the average of sigma, but we do it exactly the way we did before. The thing inside this blue bracket is just a number again. It is just a number. So we calculate the average spin given this expression for the energy, and then we set that equal to the average. We do the calculation and we get this number here, tanh y plus beta b. That's gotten by saying the spin over here feels its neighbors.
I'm just saying when you define y, it has to be equal to,
The definition of y hasn't changed.
sigma over 2b, sigma.
Oh, yes, it is.
Plus beta b. Right there, that's it. Y is still the same as it was before. I have not changed the definition of y. It's still 2b dj sigma bar. So this is tanh of y plus beta b.
But that affects the left-hand side too.
No! No! Doesn't affect the left-hand side. The left-hand side,
You're still defining y to be the same thing you did before.
yep, y is exactly the same thing as it was before, and it is the average spin. We calculated the average spin and set it equal to the average spin. On the right-hand side, we did a statistical mechanics calculation of the average spin, assuming that the average spin had a certain value. On the left-hand side, we say, well, okay, then that must be the average spin. That's why it's called self-consistent approximation. Hmm? Yeah, you're going to shift the curve. All right, so let's shift the curve. Let's shift that. That's exactly right. We're going to shift the curve. So let's see. If beta b is positive, that shifts the curve backward a little bit. Okay, that's the new curve. And now let's draw the red curves. The red curves are, the left side is exactly the same as it was before. The right side, the curve has just been shifted to the left. By how much? By beta b. By beta b. So this gap here is beta b. Beta b here. All right, we start at the origin, same curves. But now there's no ambiguity about which solution we should take. There is no solution at the origin. No solution at the origin anymore. Only these points over here for positive j. Let's say for positive j.
What happens at infinite temperature, though?
At infinite temperature, okay, so let's see what happens at infinite temperature. At infinite temperature, this gets very close to vertical, right? This gets, no. 0 temperature is close to horizontal. Yeah. Infinite temperature is, so here's our answer. Here's where our intersection is, right over here. And at that point, y is equal to 0.
Beta b will move to the right. It will shrink. Beta b goes to 0.
Beta b does go to, no. No, we're going to 0 temperature. Sorry, we're going large temperature or small temperature?
Goes to 0 and the curve shifts back to where it used to be.
Yeah. Doesn't matter. No. What do you want to do? You want to go to large temperature or low temperature?
Very large.
Very large temperature.
Beta
Okay, so beta then goes to 0. Yes, the curve shrinks back. Yeah.
If you vary the temperature, you have to shift your
Yeah.
tanh function.
Yes. Right.
So that means that even at very large temperature, even among the
You see what's going to happen. You know, you're right. What's going to happen is this point is going to shrink down to here. It's going to move to here, and
The beta b just goes to 0.
Right, so then that
Shifts it backwards.
Tangent
So you have no more magnetic arrangement at infinite temperature.
no, you have certainly not at infinite temperature. At infinite temperature, it's random. So the solution, the curve looks like this. And the solution is down near here. As you let beta get smaller and smaller, you find no magnetization, as you should for very, very large temperature. All right? But now, as you move away from infinite temperature, you see the only solutions lie on here. No matter how small, let's go to small temperature now. Small temperature, you move this way back. Okay, so you're certainly on here. And even as you go to higher and higher temperatures, you stay on this curve. You stay on this branch of the curve, although the whole thing shrinks down to here. There's no question of being stuck at this point for all temperatures. So for a randomly temperature which is not infinite, there's only the solution up here. So no matter how small you make the temperature, as long as it's finite, no matter how large you make the temperature, as long as it's large or small, the only solution is up here.
Is it clear that as your temperature gets very small, so you're moving on along the curve,
Yeah.
but the curve is moving to the left very fast also?
Not very fast. It only can get to here. That's as far as it can get.
No, it's going to the left faster.
Oh, as you're letting the temperature go to 0, yeah.
Yeah, okay.
Yeah.
So is it clear that your intersection is going to be getting closer and closer to a height of 1?
Yeah.
Yes.
Why?
As it should.
I mean, the curve
This curve just moves. I know, but it just moves this horizontal line here, just dominates
Well,
everything.
that line isn't horizontal. It's going to horizontal.
Okay.
The question is,
I know, but if you take a curve that goes to horizontal here and you shift it a lot, it's very close to
The
horizontal.
line's slope goes to 0 as well.
you got some kind of limit thing you have to prove.
Nah.
No, it's
Is the
all
external
over.
field still there?
Because at infinity, the slope of the,
What, you're not at infinity, you go towards infinity.
you just
As
push it,
as
I'm just saying
temperature-
the slope of the line is, the slope of the line, the y line is going down. Okay, so it's getting towards 0, so it's going to intersect 1 at a long
No,
distance
it's not going
away.
to intersect. It's the question is where does it intersect that curve, not where does
That
it
curve
intersect
is
what?
always just bounded above by
Also,
y.
the slope at the place where it crosses 0, the hyperbolic tangent, it's getting smaller and smaller, so it's pushing out this way also.
Yeah, two
I mean,
things
I'm
are
not saying
happening.
it's
The
not
curve,
true. I just think that there's a little bit more that has to be shown.
Yeah.
And you got a curve that's going up towards 1, and if you move that curve.
if I bring this to my car mechanic and I say, Joe, what is this going to do? My car mechanic will tell me every single time what it does. Why? Because he knows, God damn it, how cars work, and this is enough for him. Come on, what are you kidding me?
Let me put it this way. At some point, at every point along that curve, it's some distance epsilon from y equals 1, right?
Yeah.
And so if you keep moving that thing over fast enough, then even though the curve is intersecting further out,
Yeah, but the curve is moving this way.
Right.
It's moving this way, so all of it, both things are going in the same direction. Both things are going in the same direction, right? Yeah. Okay. All right, so we see just adding the tiniest little bit of magnetic field will leave only the solution up here, the magnetized solution. Yeah.
The external field is still present, right?
Which?
External field.
Yes, but the external field can be made as small as you like.
Right, but it's still present, so the
Right.
magnet will still orient.
Yes. Yes, but for arbitrarily, think about it this way. For arbitrarily small magnetic field, which means bringing this intercept here to be arbitrarily small, tiny, tiny magnetic field, much smaller than the magnetic field of the Earth, you still have only the solution up here for fixed temperature. Fixed temperature means for fixed slope here. You let the magnetic field go to 0, and you'll be on this curve.
Yeah, but the magnet still have an orientation then.
Right. Right. This is an instability. The tiniest, tiniest magnetic field, doesn't matter how small it is, it will still bias it up to here. That's called spontaneous symmetry breaking.
May I
A
suggest?
magnetic field which is far too small to measure.
May I in fact, if you look at the upper curve, which is without the magnetic
Yeah.
field, and you assume the center red point, the 0, the origin, making an infinitesimal move to the left, you see that the curve will intersect infinitesimally up on the
Here?
Yeah,
Right.
well,
Yes.
and that shows that there is a bias immediately. Infinite.
No,
so
no.
That proves your point. Even if it's just shift it infinitesimally to the left, immediately it cuts the y-axis.
The point is that this solution is unstable.
Yeah, but is it possible?
It's possible, but it's unstable.
Okay.
You add the tiniest magnetic
Yeah,
field,
I
and
understand
it will
that,
flip
yeah.
to, yeah,
I have a suggestion.
yeah.
If we absorb the d beta into the y so that we're comparing hyperbolic tangent of y
Yeah.
to a left side that has all the betas of the expression, then that left side becomes a set of lines that intercept have a y-intercept of minus b. So basically the graph.
These lines will intersect to the right then.
Well, if we look at the graph on the top board,
Here?
yeah, keep the hyperbolic tangent in the same place and then move all the red lines down by b.
Right.
Yeah, that's what
Yes.
That's what I said.
That's
Move
right.
a little to the left.
Then you'll only have the one intersection.
Then we have only one dependence on beta.
You want to keep the hyperbolic tangent fixed, right?
Yes.
Shift it a little to the left.
Right. So which way does it shift?
Left.
All the
No,
red lines
right,
shift down.
right, right,
No, it doesn't
right.
shift anywhere.
Hmm?
The hyperbolic tangent stays,
And the red lines,
all the red lines shift down by b.
Yeah, it shifts down, which means it shifts to the right.
Yeah.
Yeah.
yeah,
Same.
there you go.
So it's the same thing. It doesn't matter which way you do it.
But it's clear that there's no way of orienting that line so that it intersects the tangent at 2 points.
Yeah. Right. So that's the argument. The argument is that the solution where all the spins are equally likely to be up and down is unstable. And what that solution is it's sort of 50-50 probability of everybody being up and everybody being down. The whole world being filled with plus spins, slightly plus the whole world being with minus spins. That has an average of 0. But if you turn on the tiniest magnetic field, the difference of energies will be enormous. Why? Because you have 1 billion light years worth of spins all pointing up, and you put in a tiny little stray magnetic field, the energy of up will be much lower than down. Just because you have this great, great big number of spins. So the solution over here is just exactly what I said. It's basically all spins pointing up, or not all of them, but on the average, everything pointing up. Equal probability with average, everything pointing down. But that's an unstable situation. Just a tiny perturbation in the magnetic field will bias it. And of course, that's what really happens with a magnet, right? I mean, you could imagine that you have a state of a ferromagnet, a real magnet, which has equal probability of pointing everywheres. And then you bring it into the field of the Earth, a tiny magnet that's not that small, but you bring it into the field of the Earth, and pretty quickly that magnet knows that the Earth's magnetic field is there, and it orients itself in that direction. So this configuration where it's equally likely to be in every direction, that's unstable. And just a small stray field will, and the stronger the magnet, the more it's unstable. The stronger or the bigger the magnet, either way, the stronger or the bigger the magnet, the more unstable it is. So,
So what causes the Earth to flip its magnetic field?
I don't know. Does anybody know?
What's the question?
Why does the Earth's magnetic field flip?
I think somebody does.
I'm not sure, I don't know.
I think the core current flips direction over time.
Well, of course the current flip, but why?
Why
Because
is
the iron core is going in one direction, generating current, it flips the other way around.
Why does it flip? There's some instability. I don't know why. I don't know why. I don't know why, other than to say there's a symmetry. It could be going either way, but why it flips, I don't know.
It's very high temperature, right?
The center of the Earth,
Yeah.
pretty high.
So that may have something to do with it.
I don't know why. Somebody look it up. I'm not sure anybody knows why. You find it in your...
It may be because there's a time lag, because the Earth's field comes from the, I believe, the motion of the core, and so there may be a time lag between the field and the motion.
Why would that make a flip?
Well, a time lag can generate instability. I don't know how.
No, it's some instability, clearly. Yeah. It's some instability, and I don't know why. If somebody gets a chance to look it up, or maybe I'll get a chance to look it up, I don't know. I know that it flips, that's all I know. Okay, good. Yeah, we'll talk a little bit more about magnets, and then maybe metals. Maybe metals, I'm not sure. We'll see.
Will you know next time what the fall will be?
Yeah. Yeah.
For more, please visit us at stanford.edu.